a look at some of the ultra important things from topic 6, and then we can move into our 2 new objectives from topic 6. All right, so the last 2 things we didn't really get to this morning were to explain the use of sensors in potential divider circuits.
Morley, please come down to the office and see Mrs. Miller. Cliff Chow, please come to the office. And the Middletown Unlimited bus is here, so you need to come down to the office as well. And
Middletown Unlimited?
Thank you.
All right, so Cliff is leaving. Is anybody on that Middletown bus?
One of us is on that bus.
Not the other.
We take, there's 2 Middletown buses.
Okay.
I don't know. You know.
All right, goodbye.
I don't think that's right.
She's on my bus.
All right, bye. Bye. Now, the sensors that we need to care about are primarily just the light-dependent resistor and the thermistor. The strain gauge, yes, we learned about, but I've never seen a question involving those. The light-dependent resistors and the thermistors had very high resistance if there wasn't much light and if there wasn't much heat. And then the resistance dropped if we shined light on the LDR or heated up the thermistor. So you do need to know that with low light and low temperature, it's high resistance, and with high light and high temperature, it's low resistance. And then the final objective was to solve problems involving electric circuits. So that would be, Ohm's law type problems, voltage drop and current type problems, series, parallel, combination, all that good stuff. Follow-up issues from anybody about the Ohm's law, EMF, internal resistance, circuits, topic 5.2. Okay. Now, as far as topic 6, right, we've only been doing it for like 2 weeks, so I don't really feel the need to review. However, I graded your quizzes, you're not getting them back today. Way better than the last one, all right? The vast majority of you did know the unit that gravitational field strength or electric field strength was measured in, and we were quite successful in finding how far from the proton we had to be for number 2 also. So way to improve over the last quiz. And just know those definitions, right? Know the equations for those 2 things. Know that we're talking about here, not the mass that's creating the field, but the mass that's feeling the field. And here, this is the charge that's feeling the field, right? Not the charge that's creating the field. So just be very comfortable with all 6 of these variables here. Other questions involving topic 6.1 and 6.2? Okay, great. So we already talked about the format of your test for whatever we meet next. Any other kind of old stuff, questions before we move into the first 2 objectives of topic 6? Yeah?
Wait, for the test, will we have to know the Earth's radius?
You have to do the Earth's radius. No. No, you need to know when do you need to add that to the distance that the thing is from the Earth and when not to. But no, you don't have to have the Earth's radius. Other issues. Okay, the only other thing there's 2 other things I can think of that are kind of old things. Number 1 is your design labs. I don't really want to count them for second marking period. I don't really want to hold off from grading them either. I'm grading sophomore lab reports right now, but I have like 1 left. So I probably will start grading the designs soon. But I think we have lots of grades for second marking period, particularly in labs, so I'd rather hold off on counting that until 3rd. And then the other thing I have in mind is just, again, midterm review. So I had very few requests from you guys and from the other section. The requests that I had were for a study guide with 1 or 2 questions, like from each of the packets. I'm not doing that.
Radhika, Agni, and Sarah Camilli, please come down to the office. That's Radhika Gupta, Abhinana, and Sarah Camilli.
But I did provide for you a bunch of questions from each topic, right, which are, I call it essential questions. And then I put your names next to a couple of those questions, so you need to at least answer the ones with your names next to them. Like write in that Google Doc, right? You'll insert a comment with your answer. So please, if some of you could try doing that, maybe this afternoon or tomorrow, that would be great. So if we have problems with that, we can hash those out way before the midterm. I was asked for an outline of what we've done. I will be putting some slides, some review slides together, which will essentially just be an outline of what we've done, so you'll have that. And then I was also asked for a list of terms, like last year, and no, the reason I won't do that is last year I had a pretty finite pool of questions that were fair game for your exam. For this, like, I don't. I mean, it's just like 8 years worth of IB tests, and I'm not going to go through them and write down every single term that's there. So sorry that one I'm not giving them. And then we should have at least 2 meetings next week prior to the midterm. So I'll plan on spending probably a third to half of each of those meetings kind of doing some review and taking a look at that outline. Yes, Dave?
What day are we going over the essential questions?
What day are we going over the essential questions? I'm not sure we're going to do that in class. I'm kind of envisioning just all of that being like in our Google Drives. If I don't like answers, I will reply to the comments so everybody can see that. But I'm actually not planning on doing them like orally in class like we did last year. Any other kind of old stuff questions? Okay. That brings us to magnets, which we have really not ever talked about. So a magnet is just a name that we give materials that produce a magnetic field. Right? So we've talked about gravitational fields and electric fields over the last couple of weeks. Right? We have our third type of field called a magnetic field. Now, some magnets are made out of materials whose little electron orbitals can be easily aligned. So some examples of materials whose electrons we can align pretty well are things like iron, right? Like the cheapest magnets, like probably refrigerator magnets, are just made out of iron. Nickel, cobalt are good elements that we can align their electrons. Aluminum is actually another one that I don't have up here. Most magnets that you find in like science labs are called Alnico magnets. What does that stand for? Aluminum and nickel and cobalt, right? So so these magnets would be an alloy of those 3 metals. An alloy means they're not like chemically bonded to each other. We just kind of mix them together. And then the strongest magnets that we find in science labs, like the ones that are holding up the poster over there, are made out of some of the rare earth elements, like these guys.
Corey Clough and Orly White, please come down to the office. Corey Clough and Orly White. Thank you.
All right, and then what's wrong?
My mom is here. Like, she's told me like 10 minutes ago that she's here, and they still haven't.
Does she know to come in?
I think so. She's picked me up questions.
There's probably a long line, right? Yes.
I think I had a bunch of like those buckyballs like neodymium magnets.
Do I know the what?
Like there's like a product. There's like a bunch of these like little magnet balls
Okay.
made out of neodymium. I don't know if I still have them. But
Yeah, bring them in. Yeah, why not? Let's take a look at them. And then all of these magnets, right, have 2 poles, right, that help produce their magnetic field. And sometimes we call one of the poles a north pole and the other pole a south pole. Or here I'm using terminology north seeking pole and south seeking pole. We can use either set of nomenclature. It doesn't make any difference. All right, so you each have your own little compass that is supposed to help us find the Earth's magnetic north pole.
All right, this time we need Nick Lursky, Phoebe and Gregory Mack, Emily Kwan, and Allie Baser. One more time, that's Nick Lursky, Phoebe and Gregory Mack, Emily Kwan, and Allie Baser. Please come down to the office. Thank you.
we just lost half the class in 10 minutes.
I was amazed how many of you showed up. Well, it probably happened to some of their parents, like, I aim to come, like, right at the end of lunch, but then, it takes a few minutes, right, to do that. You're going to be soon too? All right. So hopefully you used your compass to find that the Earth's magnetic north pole, this one doesn't work, is somewhere that way-ish. This one doesn't work. That way? Really?
I'm getting.
Yeah, it's a little closer to this way today. Hi.
Nick was a little too excited to leave your class, and his face lit up.
All right, folks, there there are 2 Middletown buses outside. If you ride a Middletown bus, please come down to the lobby. Thank you.
That's not you? Do you live in Middletown?
No, I live in Freehold.
Oh, I thought you lived in Middletown. All right. Anyway, let's talk a little bit about the Earth's magnetic pole before we go any further. I get so disoriented. The parking lot's right over there, right?
Yes.
And then, do I have it right then that Kozlowski goes this way?
Yeah.
Yes.
Like pretty much perfectly this way?
Yeah.
And I also kind of feel like Kozlowski is parallel to Route 9. Is that kind of right?
Because
Kind
it current,
kind
like,
of. All right.
it's like current.
Well, anyway, I don't know that that's helping illustrate my point. But the Earth's magnetic pole, my compass is saying, is kind of that way. But that's not in agreement with the geographic North Pole. All right? So the Earth does have some churning stuff in our outer core that we believe is responsible for the magnetic field that the Earth creates. So, oh boy. Not awful, right?
No,
Pretty bad.
pretty
Not
good. It's good.
totally awful. And the equator, I don't know, somewhere over here. I probably shifted everything down a little bit. So our compasses don't actually point towards here. Now this would be like the rotational axis. So the planet like rotates this way. So the geographic North Pole would be that spot that you could stand there and you would kind of just rotate perfectly like this right there. Oh, what else would be neat there?
The sun wins.
The sun, right, is kind of out for 6 months straight and then like gone for 6 months straight. So whatever. That's not where our compasses point. Our compasses point, oh, I hope I have this right. Our compasses point kind of like here.
Yeah.
Right? Because our rotation has really nothing to do with the magnetic field produced by the Earth. So it just happens to be that the magnetic field of the Earth emanates from this spot, and it just happens that that's sort of close to the geographic North Pole. But that's not always true, and the magnetic pole migrates quite a bit. It even flips every 10 million years or so. It switches, right? And the North magnetic pole would actually be kind of close to the South Pole. So the two really have no relation to each other. If we were to walk in the directions that our compasses are pointing here, that points about 12 degrees away from true north. So if you're like lost in the woods and this is all you have, you can roughly be going north. I have a compass app on my phone that I think I played with a little bit, I don't know, over the summer. And I just opened it up earlier.
Jeffy Lou, Miles Colombo, Emily Triolo, and Daniela Tsang, please come down.
So I have like a, oh, that's you. This compass app that doesn't point the right way. It actually tells me north is like that way. And I don't know why that is. I don't know why that is.
It's pointing south.
Anyway, so the Earth acts like a magnet, right? Fine. Here are some other models of magnets that we often find in science labs, and these are sketching the magnetic fields onto the magnet. So this would be the classic kind that we typically use. It's called a bar magnet, right? And this end of the magnet is called the North Pole, this end is called the South Pole, right? And we see that there are nice field lines that leave the North Pole and then enter the South Pole. This sort of kind of looks like our field that we had from electric charges when we had a positive one here and a negative one here. But it's not really the same thing because we do have field lines that enter and exit like the middle of the magnet as well. But it's very reminiscent of our electric fields. For our horseshoe magnet, right, one side of the horseshoe is the North Pole, the other side is the South Pole.
Tamani, Johnny, please come to the office. Tamani, thank you.
Right, so we still have magnetic field lines, but the geometry is quite different. And then this is a little disc magnet, right, like the ones that are holding that poster up. And one end of that would be, let's see, which one is north? I guess this end is north, and then this end is south. So we do have field lines that lead from the north to the south. All right, so again, a magnet is just the name that we have for things that produce a magnetic field. Questions from anybody about these kind of semi-permanent magnets? that are producing these magnetic fields. Right. We actually don't really do much with that type of magnet in this class. Because that's actually really complicated. That's way more complicated than the type of magnetic fields that we're going to deal with. So we have known about this link between electricity and magnetism for closing in on 200 years now. All right? They were kind of viewed as two distinct phenomena, at least in Ben Franklin's time anyway. But right after Ben Franklin, right, Ørsted was able to prove, right?
Alex Silverstein and Alexandra Iglesia, it is your turn.
Was able to prove that there absolutely is a very strong link between electricity and magnetism. In fact, the only thing in the universe that creates magnetic fields is moving charges. All right, moving charges. It has to be have a net electric charge, and it has to have a velocity. If we have those two things, then by default we're creating a magnetic field. So what we're going to start with in our first objective here, our first two objectives, is dealing with charges that are flowing in a wire, right? Because then we really only have one direction's worth of velocity that we have to care about. All right, but any charge that's moving creates a magnetic field, and that's the only thing that creates a magnetic field. Questions about that before I actually go backwards and ask you guys a question? Yes.
So like in bar magnets,
Yes.
there's electrons.
So Justin wants to know about the bar magnet. And what was your proposal for the moving charges?
That do the electrons like move?
So do the electrons kind of going around their nucleus? Well, that certainly is a moving charge, and they would have an electric field in that sense, or a magnetic field in that sense, but that's actually not why that thing acts like a magnet. That would be the most logical reason. But as it turns out, we can't really make the electrons in each of those atoms like move in the same way. The repulsive forces as the electrons get close to each other are just too strong. We can't align them to do that.
All right, gang, we have 3 buses outside. We've got Durham 419, Durham 433, and the Howell bus. Durham 419, Durham 433,
Who's gonna be last?
and the Howell
Oh,
bus.
our bus.
Probably.
Our bus like leaves at 1:30 and they get here at like 2.
Well,
yeah,
it would
Justin,
be
our bus
awkward
is
if it
really
was
short.
me and one of you, but as long as it's 2 people.
Well, we're closer to Noah, it's 1 o'clock minute.
There's
Alright.
another cool circle.
Whatever. So anyway, we need to address what Justin brought up, right? So it's not the orbiting of the electrons that's creating the magnetic field, it's actually their spins. And when I spin myself like this, that's a little bit disingenuous, but not exactly what the physics quantity called spin is. That's what we call it. But we can align the electron spins. It's not the orbiting, it's a different aspect of the electron motions. But yes, it does have to do with the electrons in here that are able to align those spins to spin in the same way. And then each little magnetic field from each electron that's doing that adds to each other to produce a pretty strong magnetic field. Other issues before we start looking at our wire. All right, fantastic. So this is supposed to be like the cross section of a wire, where the wire is the little black dot in the middle, and we have charges moving like out of the board and then into the board. And then these concentric circles with an arrow are supposed to be representing our magnetic field lines. So the magnetic field produced by charges moving in a wire, right, resembles these concentric circles, right, that go around. And there's a couple of things that we want to be able to recognize from this diagram. Number one, it is meaningful that there is less space between these two field lines than there is between those two field lines. Right? The magnetic field further away from the wire should be weaker. The magnetic field closer to the wire should be stronger. And just like for electric field lines and gravitational field lines, it is the field line density that tells us something about the strength. So the two really important features of the magnetic field around a wire is that the field lines get drawn as concentric circles, and the circles get spaced out more and more as we move away from the wire. All right, once you guys finish writing whatever you're writing, let's come up here. Bring your compasses.
Oh, so much space.
You all right? I'm gonna try and look straight down if I can. That's good enough. Come on this side.
2.
All right. All right, so let's take a look at the circuit that we have. So we have a 6-volt battery, right? This is a variable resistor. Right now I have it on 100,005 ohms, just in case somebody closed the circuit. I didn't want much current going through. We have a switch, which is open right now, so there's no current going through anything. And then we have a compass here. But I'm definitely interested on placing more compasses around. But first, let's take a look at what happens to this compass when I lower the resistance of the variable resistor and then send some current through it. I'm going to try and zoom in a little bit on that.
Just to clarify, bus number 433 is Cold Connect, okay? If you ride 433 to Cold Connect, your bus is here.
All right, and then on the video, you actually can't see the white part of the arrow, but you can see the part that points kind of south. And hopefully, we're going to see that rotate to some other direction when we turn the current on. All right, so I'm going to change the resistance. Now, when I close the switch, we only have 5 ohms of resistance here, and then whatever the resistance of the wires is, and the internal resistance. So we should have a lot of current. All right, here we go. 1, 2, 3. Did it change directions?
Yes.
It did. It changed by, like, how many degrees would you estimate?
30, 15.
Yeah, 20-ish. 20-ish, right? And that's actually with a lot of current. So we actually do need a pretty strong current to produce a sizable magnetic field. And if we move this further away, I'm actually not going to move it further away from this one. I'm just going to set it underneath this wire, but now it's quite a bit further underneath, then we might not notice anything at all. We might not notice any effect at all because it's just way further away from the wire now, and we know the magnetic field shrinks as we move further away. Has it kind of steadied? Yes. I saw very little. I saw something, but maybe 2 degrees max, right? So the magnetic field really does diminish quickly as we move away from the wire. Other questions about what we just saw here? All right, stay here.
So it's like exponential.
Is it exponential? Think that it would decrease. I think it's going to be, is it going to be inverse square? I want to say it's inverse square, just like our kind of gravitational force and electric force, but I'm hesitating. I'm not positive that that's right. All right, let's stay here. I want to just see what my next slide is. All right, we'll stay here, right? Because there is a lot of room. So here's a couple other diagrams of the magnetic field around a wire. All right, so we have the one on the left, which I like because it is showing us that it's not just one spot on the wire that's producing the magnetic field, right? It's like every spot we would have these concentric circles, like at every spot of the wire. And then...
Okay, got a big group here, so listen up. I need Patrick Rogers, Kevin Keneally, Stephen Petridis, Sophie Smith, and Connor O'Leary. That is Patrick, Kevin.
Battery's gonna die soon.
Sophie and Connor, come down to the office, please. Thank you.
All right, and then we have the other diagram with the green wire, and I'm saying to identify the problem with that one. So who sees it?
Very evenly spaced.
Yeah, those field lines, which are concentric circles, are evenly spaced, and that's not good, right? The outer one should be further away than it is. Now, there's some letters up there, right? In fact, is it just coincidence that they're I and B, or are these like official IB diagrams? Well, the I stands for current, right? And then guess what the B stands for? Magnetic field strength. Yay, Leia did some reading ahead. Right, so B stands for magnetic field strength. And notice that on the diagram on the slide before and on these ones, we actually do have arrows on the field lines.
Last call for the Howell bus. We're missing freshmen Lexi and Jenna. This is the last call for the Howell bus. Please get down here right away if you're still in the building. Thank you.
Alright, so there's one other slightly weird feature in these two diagrams. What is it? One of them has a hand, right? And it's not just given like the thumbs up. The hand is actually there for a reason. Because, are you all right-handed? Anybody left-handed? You're both left-handed? Alright, you're out of luck in this unit. Because we have a number of right-hand rules. They only work with your right hand. So here's how this first right-hand rule works. It actually allows us to put these arrowheads onto these field lines. And I probably have this on the next slide. Yeah, good enough. I'll go back to that after we've done it, if you want to jot any of this down. So we take our right hand, and we either literally or metaphorically wrap it around the wire. Right here, each of you take a wire, right, and unloop the wire so that it's not the two ends aren't attached to each other. For those of you at home, right, you can get a wire too, just find a cord from something. So you gotta use so hold it in your left hand, right, because we need to use our right hand, right, and you take your right hand and you literally wrap it around the wire. Well, you wrap it around the wire so that your thumb points in the direction that the current is moving. So for me, I'm assuming my current's going up towards the ceiling, right, so I pointed my thumb up. All right, and then the direction that your fingers are wrapping around the wire is the direction that the field lines would point, right? And I don't know if these do a very good job of showing it. I guess they do. So in this one, right, we wrap our hand around the wire, like metaphorically, and on this side of the wire, right, my fingers are like on this side. So my fingers would, this is very difficult to say, but the field lines would be going around in this manner. Right? In front of the red line, they're going this way. Behind the red wire, they're going that way. Right? And I don't have a great way to describe that. If you just look at the piece of the wire that has your fingertips, right? Your fingertips would point in the direction of the field line. So you can always just rotate your hand until you get the direction that you're looking for. And I think we'll wait until next class to kind of test that out and make sure that that works. Now that's great for a vertically oriented wire. Why don't we